So all the problems that we've had so far, for example these, always had completely symmetric loading, therefore the reactions were split equally into two, right? We didn't even have to think about it. But once you start having a asymmetric loading, for example you have more here, double the load here, then obviously your reactions isn't going to be equal on the right and left. And I mean, you can, so this is just as if you had a beam, right? Whoops. If you had a beam with same exact span and same exact loading pattern, then you can basically determine what the reactions are, right? So for those of you, I mean, even if you didn't take structure 1 with me, you did this before, so you can actually calculate by doing the math. Right, basically distance times force, distance times force, etc., like from the left side. So basically, if you keep doing the calculation, so in this case, you know, 5,000 times 12, this times 24, this times 36, this times 48, this times 60, this times 70. That, all of that addition should be equal to this times 72, right? So you can eventually get the number for here, and this one is all of that addition minus that. So you can do that long calc, but for those of you who did structure 1 with me on this beam problem, some of you didn't take it, so I will show you a quick way, which is kind of fun. And it's recorded, so I guess it's good. So what we're gonna do, so I mean you can calculate, let's just do that calculation thing. So if you, and I lost the distance, right? That's great. So yeah, I have distance, so you can calculate by doing 12 times 5,000 plus 12 times 5,000 plus 24 times 10,000 plus 36 times 10,000 plus 48 times 5,000. Oops, sorry. 48 times 5,000 plus 60 times 5,000 equals R2 times 72. Simple calc, but I'm not gonna do it. So that's one way. Another way, which, so I'll show it to you guys who didn't take structure 1 with me, is to kind of similar. We can do it completely graphically. I'm just gonna need these lines for later, but first thing to do is I'm gonna copy all of that, 5,000, 10,000 in order. So I'm gonna connect all of those in order, right? just like we do for the trusses. So we have one here, second one from here, third one from here, fourth one from here, fifth one from here, right? And then reaction's gonna be somewhere, but we don't know. What you can do is put a random point anywhere in space, really doesn't matter where, and you can connect that random point to end point of each of these arrows. And so you end up with this fan looking thing, and it could literally be anywhere. It could be here, it could be there, it could be there, it could be there, it could be there. But the more skewed the form is, it's going to be really hard to read your diagram, so I tend to like somewhere, not there, but something like this, something that's even. It's also, I can share this script. It's also helpful to color these lines, just to be clear. So just for the sake of demonstration, I'll do that. Again, actually, it's still helpful to name these areas. So I would call it A, B, and this is not to be confused with those areas that we're gonna name when we solve the trusses. All I'm doing, this is just to get the reactions correct. And G is actually this entire zone between R1 and R2. So therefore you have, it's supposed to be uppercase, but I'm just gonna copy these right now. A, B, C, D, E, F. Makes sense, right? And basically all of that, A, B, C, D, E, F, that's supposed to happen here. So A is gonna go here somewhere. Right? Yeah. B gets cut here. C is gonna move here. D is gonna move here. E is gonna move to here. I'm gonna trim it. F is gonna move there, and ends here and ends there, right? Because there's R1 and R2 here. So this is supposed to form a closed polygon. So what I'm gonna do is connect this endpoint so that this gets closed, and that line that we just drew to close this polygon, that if you look at this zone correspondency, A was here, B was here, C was here, that corresponds to the G, which helps us identify R2 and R1. So what I'm gonna do is just gonna bring this back to this point on the force diagram, and wherever that intersection ends up being, that's where point G will be, and that is gonna determine the size of R2 and R1. So now what's gonna happen is if you connect point F and G, which is basically going from F to G, so this is going to be called FG. So that line that I just connected between F and G, let me just move to the side, that's going to be a reaction 2, and then the next one would be from G to A. So that's going to determine the reaction 1. So this is reaction 2 because that's FG, and next one is R1, that is GA. So again, if I were to get the length, this is 50 inches, 5,000. So if this is 166 inches. So it's like 16667 pound. I think I wrote it somewhere. So yeah, so that would be a reaction 1. And that would be a reaction 2. And of course, the total of reaction 1 and reaction 2 should be equal to total of 5,000, 10,000, 10,000, 5,000, 5,000. So it's total 35,000. So if you add this and this, it's 35,000. So that's how we can graphically determine, the reactions. Either that or doing this calc. I mean, it's actually, that's a simple calculation too, so it's equally fast. Anyway, so that's how you got the reactions. And again, going back to the truss, right? So if you, hold on. Right, so now if you go back to the truss, you do the same routine of mapping the zones between the forces. So actually, if you notice, the A, B, C, D, E, F, G is exactly the same as we drew on this side. So except that, right, like compared to the previous problem, of course BC is longer because that's longer, and CD is longer, right? Anyway, and then you have these reactions, and then you name the zones in the truss just the same way. And if you follow the same step, because the point A, B, C, D, E, F is distributed differently on this right side, it's gonna slightly differ compared to, for example, this problem, right? So I guess hopefully that's enough, right? But you start seeing where point 3 and point 10 doesn't match, and so you might wanna try to draw one of these diagrams. But that's the only thing that's different. This start point, how they're distributed, it's gonna affect whatever end up. But the process to draw this is exactly the same as the previous truss problem. So is that good? Okay. Wait, we have to 11:45 actually. Okay. But yeah, if I start drawing all of these, I think we're gonna use up the 30 minutes. So yeah, so try drawing that. So obviously, if I compare this with the original truss problem of like the same exact loading, if I compare that diagram to this here, see how on this side all of these were equally 5,000, but now this and that, whoops, and hold on, CD is this guy, so these two got longer. So you see how the entire diagram got longer, and yeah, so that's the difference. Like 310 starts to split, 58 starts to split, and so location of these points are slightly different compared to the last one. So that's kind of what's going to happen. How the beginning is set up differently, that's going to affect how this is going to turn out. So that's that. Now going to the various trusses problems on here. Alright, so we can look at whichever one. So I already explained it in the video, this one, so you can watch those. that one's probably is gonna take longest. Should I do that? It's probably gonna take more than 30 minutes. So it's either I'll try to do this super quick and you might get lost, or any preference on which one? No? I guess I can do the triangular one because it's, well, yeah, that's gonna take a while. I know that. Let's see, is it this one? This one has been symmetric various. So let's see. But I can skip a process. Alright, so I'll try to show you that K-truss which is gonna end up looking like this. So yeah, let's see if we can do that. So again, so numbering alone takes some time, but A, B, C, D, F, G, that's the same exact thing, but I'm gonna name each of these areas, right? Now, same thing. I think I'm gonna cheat on this side too. You can do, right, so same thing, right? So A, we don't know where 1 is yet, so that's G, that's F. So I'm gonna have A, B, B, C, same thing, C, D, D, E, E, F, which are all equal to all of these, and then I have FG, which is halfway, GA, which is halfway. So that's straightforward. Again, as always, you start from here. Right, so maybe I'll do it halfway and then I'll show you how to read the diagram. So I'll start here, or actually I'll start here, going this way. This we know, which is G and A. This one, that part right here is A1. A1 is supposed to be vertical, right? So I'll copy something here. And change the color. Yes. Dashed line. So 1 is supposed to be somewhere up here, but we don't know. So we're done with this one. So we're gonna go to moving around here. So only thing next is this one. 1G is horizontal. So again, we know there's something here. So that's here. Then you're forced to think that 1 must be on here because 1 and G intersect. So we are done with that. Moving on to next point. Here it's 1A, same thing. That's A3. So A3, 3 is on here somewhere, but we don't know. Right, so actually I should split all of that to, so that's A3. This is 3, 2, so there's gotta be, so 3, 2 is somewhere here. But 3 we don't know yet, and 2 we don't know yet either. So that's kind of unknown and unknown. That is 2, 1. So it's going to go through 2 and 1. And so 1 we know. and now that's gonna help us fix the 2, right? No, not really, because we don't know the 3 yet, so it might actually be sorry about that. So 3 might still move around up and down. So 2 is intersection between this line and some unknown line yet. So that much I can tell from this. And this is 1A, so same thing. So that's kind of all we can tell from that point. So moving on to the next one, 3A is vertical. Again, same information. This is A3 horizontal, which is going to help because then it's on this vertical line and also on this horizontal line. So the only choice actually is A is identical to 3. So that's gonna force this line to here. Then it's gonna actually help us locate the point 2, which is on the intersection. So that was that for here. So that's A3 and that's 3A. So that's all I can tell from here, and we're gonna move on. So I'm gonna delete this too, A3 and 2. So this is G1. That's there, 0. So actually, so what we know already is G1 is 0. So there's no force apparently. On here, or 1A has some force. This is 3A. 3A is also 0. So is A3. Yeah, so that's good to know. Anyway, here 1, 2 is there. That's we already have, and that vertical is 2, 4. So there's gotta be some vertical along 2, and 4 should end up somewhere on here. 2, 4, 4G, 4G, it crosses G, so the horizontal line 4 is also on here, so we're forced to conclude that 4 is at the intersection here. So you keep going. I mean, you see kind of a pattern that's here, right? So you keep kind of repeating. Typically, if you have this sort of symmetric force, symmetric form on the truss, I mean, one thing you know from before is the top chord is always compression no matter what. Bottom chord is always tension. I mean, as long as the loading is from above, which is typical. So you see, you have a pattern of forces where it's like same direction gets smaller and smaller or bigger and bigger, right? So that's why you get these form diagrams. So once you start drawing something like this, you know, you get to a kind of repetition where these are proportionally keeps getting smaller, and your force diagram should also be symmetrical if the truss is symmetrical. What's kind of important here is that the zero force member is kind of important. So here you can see these 3 don't matter. So it's actually the same thing if you had something like this, which you, whoops, not that guy. But if you had something like this, it's gonna do the same exact thing because this zero force member is not doing anything. Was kind of the same thing as you had on these guys, right? We had zero force member here, so it would be the same story if you had something like this. And in the case of this guy, it would be the same thing as if you had this. And the thing is, you see this kind of truss a lot. And actually someone asked me last week about these, right? So for example, if you compare this diagram here and the one that's hanging actually above us, is you see how the bottom cord is not touching the wall, or you don't see any vertical support column or anything that's supporting that bottom cord, right? Because that particular portion, that last segment of this bottom cord is precisely what this guy is, which is zero force. So you actually don't need to connect that to a vertical support. What must be happening is there's got to be a column or post of some sort behind this wall that's supporting the top cord of this truss, but the bottom cord at the end is not really touching anything. So when you see something like that, you should know that's so this kind of pattern should be fairly familiar to you guys. I guess 20 minutes more. I could keep going with this guy. Where did it go? Oh, alright. So we were up here 4G was up there, and G1. So we move to the next point. That's 5-4. So therefore I'll copy that and call 5 would be somewhere. That's this one. This one is 4-2. We already have that. That's 2-6. So that means 6 is somewhere along this line. That's 6-5. 5 we don't know, so it's gonna be anchored to a point where we don't know yet. So that doesn't really help. So I'm gonna move on to the next one. I'll do this pretty quickly. This one is between 6-2. So 6-2 we know that's vertical. 2-3 is here. 3A we already identified. B6 is something that would be helpful. So B6, so this is B6. That's going to be a horizontal line that's starting from B, and it's going to end at 6, and 6 is on here. So 6 must be at the intersection point of that guy. Let me trim all these unnecessary portion of these lines. So now we lock down 6. Right. So now, because we locked down 6, we know. Actually, we can go back to this point where we knew this was 6-5. Which is going to be passing through 6, and 5 was on here somewhere, but now we know 5 is on here somewhere too, so the 5 must be on the intersection point. So now we're gonna move on. So now I'm already starting to see this pattern where did I mess it up? 6, 4. Right, I'll double check on that one. 6b, no, this is wrong. That's wrong. 4 is on here. 6 is on here. That makes sense. Anyway, so I'm starting to see this repetitive kind of thing, right? So it's just, I think yeah, it's just gonna take time. So let's see, how many people submitted? So do you think you guys will be able to submit this today, or do you guys need more time? The original one, the 4 questions. Hmm? More time? Okay, so sample problems. I forget words. I'm sorry. But yeah, this one. Okay, so it's basically 4 problems. So. So basically for December 12.
December 12th?
No, sorry, February. Why do I keep saying that? February 12. Well, so one thing I need to figure out is like what's the right amount of problem to do in 1 hour. 1 hour, right? 45 minutes. Is it 45 minutes? 1 hour and 15 minutes. 75 minutes. So how long did it take you to do one of? It took 1 hour to do one.
Yeah.
No.
Yeah, around there. I mean, we gotta go back,
I had
check
to go
it.
back and check the one before.
Yeah.
And the TV's on.
It's multiple choice. Multiple choice.
You can squeeze it in too, but it's risky.
See, it takes time, and it takes a lot of time for me to explain because like I'm explaining every single part. But if I do it, it's actually like fairly quick. So. Hmm?
3 problems? In an hour?
Yeah, that sounds good. Yeah, so one, I mean, at this point, okay, so at this point, it doesn't make sense to do this symmetric loading, right? Because I assume you're really familiar, like you can draw this diagram. So what if I had one problem with asymmetric loading where you have to find the reactions, also complete the diagram, and then maybe it would be, maybe I won't ask you to identify forces in like all of these, right? Hmm? Yeah, or maybe like 1, 2, 3, or maybe like 1, 2, 3, right? So maybe not all, I don't know how many, 1, 2, 3, like all 13 of them, right? So I'll have one asymmetrically loaded truss of this type, where you would, I mean, you have to obviously complete the diagram and then get the forces here. So that's one. I might ask for the reaction too. So that's one question. And then it would be a random one out of these. That should be fair, right? I mean, should I do it next class? Or 12s?
No, for 12.
12s, okay. Okay. Okay, so now, in order to make the next class productive, you guys should have questions, because I kind of feel like me explaining from scratch in front of you guys is kind of useless. I can do that in the video. So actually, so that's great that you pointed out the wrong answers. I'll probably spend next 15 minutes correcting that. So otherwise, yeah, have questions. That way, if you had actually asked questions, if you asked questions here beforehand, right, or email, then I can come prepared with what questions to answer. Because it's like teaching you things is one thing, but getting a grasp of what you're getting and what you're not getting, what's hard and what's easy for you is another part. Like I need to make sure that you can get this, and because my goal is for you to be able to look at the trust and solve it really easily and then understand it. That's my goal. Not necessarily the test, but that's actually kind of a good opportunity for you to force you to get it. So otherwise I can end this.